All right, let's take a look at a sample problem that is associated with Section 2, vector operations. Here we're going to be finding resultant magnitude and direction. This is going to be very important because these resultants are typically going to be representing vector quantities. Obviously, this section is about vector operations, so we're dealing with vectors. Vectors have both magnitude and direction, as opposed to scalar quantities, which just have magnitude, no direction. Remember, it's the difference between distance traveled and total displacement, or the difference between speed and velocity, right? Scalar versus vector. So here we have a sample problem that reads, an archaeologist climbs the Great Pyramid in Giza, Egypt. The pyramid's height is 136 meters and its width is 2.30 times 10 to the second meters. What is the magnitude and the direction of the displacement of the archaeologist after she's climbed from the bottom of the pyramid to the top? So again, talking about displacement, there's going to be a magnitude and a direction. So first thing that we're going to do is we're going to define some stuff, okay? Meaning, let's take stock of what we know. We know that we've been given a delta y, it's 136 meters. We've also been given a delta x. Here's a little bit of a tricky thing. That's going to be the width of the pyramid. Okay, we're actually only going to take half of that, right? The 2.30 times 10 to the second meters. Well, we're trying to climb to the top of the pyramid, and you guys know that the pinnacle of the pyramid, the zenith of the pyramid, is halfway. It's a radius as opposed to a diameter. I know that's not technically accurate because it's not a circle, but we're going to take half of the width. Okay, so our delta x that we're talking about for the archaeologist is going to be 115 meters. What we don't know is the resultant. Okay, and we're going to represent that displacement, the resultant of the displacement as d, and we don't know the angle, the direction, okay, represented here by theta. And so what we first need to do here is define a coordinate system. Okay, and you're going to have to draw a picture in order to do this. And trust me, drawing a picture is going to be how you get through these types of problems. So we're going to choose the archaeologist's starting position as the origin of the coordinate system, as you can see on the screen here. If we do this, we can map this to x-axis versus y-axis. Okay? And then we can start to label the things that we know because we've been given stuff, and we can label the stuff that we don't know, what we're being asked for. You can see here that we have a delta x of 115 meters. We have a delta y of 136 meters. Here is our angle, theta, and here's our resultant represented by d. Next, let's plan out what we're going to do. So first off, we need to choose an equation or to understand what situation we're in. Here, the Pythagorean theorem can be used to find the magnitude of the archaeologist's displacement. The direction of the displacement can be found by using the inverse tangent function, as you can see here. So we can rearrange these equations to solve for the unknown things that we want. Okay. So here is our Pythagorean theorem, good old-fashioned Pythagorean theorem. Well, if we're trying to solve for this resultant d, we can square root both sides, and it ends up looking like this. And you'll actually see this is what I use when working out practice problems in this chapter. We do know, based on the diagram that we drew, that the tangent function of the angle is going to be equal to delta y over delta x. We know that because tangent is opposite over adjacent, right? That's why delta y is on top and delta x is the denominator. If it was a different angle, the delta x could be on top. But again, that's why it's so important to draw your coordinate system and draw your diagram so that you can take care of knowing which value needs to be a numerator and which needs to be a denominator. But I'm not just trying to find the tangent of the angle, I'm trying to find the angle itself, theta. So in order to solve for theta, I need to take the inverse tangent, okay, inverse tangent, that's why it's tan to the negative 1, of that same fraction. Next, we can actually start doing our calculations. So we have the equations that we're going to use. We have the Pythagorean theorem right here. Well, I'm going to plug in my delta x. Remember, it's half of the width of the pyramid at the base because we're only going to the top of the pyramid. We're not going all the way around the pyramid. Squared plus the height of the pyramid squared. Now, some simple calculator work will let you know that's 178 meters, the three significant figures. Solving for theta, we have the inverse tangent function of delta y over delta x. Well, that means that we take 136 meters divided by 115 meters. There should be a meters in there. And simply plugging that into the calculator, make sure it's the inverse tangent function, okay, not the regular tangent. But if you do that appropriately, you'll come up with 49.8 degrees. Again, 3 sig figs. Step 4 of any working in a problem, we need to evaluate. So let's kind of check our answers, broad strokes. Because D, the resultant, is a hypotenuse, the archaeologist's displacement should be less than the sum of the height and half of the width. The angle is expected to be more than 45 degrees because the height is greater than half of the width. And these things make sense. Okay? These things make sense. So we're pretty confident that we didn't mess up anything major, because we did mess up something major. These kind of broad stroke checks, they would show that our answers didn't make sense.